All right, so this is part 2 of Unit 2 notes. And so we're starting here with average velocity where we paused on the last video. And so if we go back and realize and talk about velocity, we're going to be looking at some sort of rate. And when we deal with a rate, usually we're looking at displacement. So we're looking at how far did something go over time. And so we use displacement because we usually have a final and we have an initial and we can put it over some form of time. And so that x that you see here in this equation, it just indicates the motion along the x-axis as if we were graphing. And so we know that displacement is looking at length because the measurement is in meters, but we're also going to measure time, which would be usually in seconds. And so we know that velocity SI unit is meters per second, and that's where it comes from. And so when we look at average velocity, let's say that they already have it graphed, what we're going to do is we're going to pay close attention to the slope. And that slope of the line in a certain position over time graph will give us average velocity or allow us to calculate average velocity. Average speed is a little bit different. However, it's going to use the same SI, or like the standard instrument measurements as velocity. So it's going to be distance over time, but we're also going to use that meters per second because distance is in meters and t is in seconds, so time. Whenever we look at speed, we know that speed doesn't have a direction, but it's always expressed as a positive number. And so when we look at this, neither our average velocity nor average speed can give us details about the trip described. So think about as you're driving and you're thinking about speed. So whenever you hit the gas pedal, you're going to increase your speed, but when you hit the brake, you're decreasing. So with speed, it can go positive or negative. When we look at instantaneous velocity, which is the next slide here, it's going to limit our average velocity as the time interval becomes infinite, so infamously short, and the time interval approaches to 0. And so the instantaneous velocity indicates what is happening at every point of time. So if you look at this graph, this shows you that if you look at B, it's going to show you at those different points of time. And so that is showing you the instantaneous velocity in the form of a slope of the line. Okay, and that line is going to be tangent to the x versus t curve, so your distance versus time curve. So this would be the green line. The light blue lines show that the change in time gets smaller and they approach the green line. And so there is, of course, an equation that goes along with instantaneous velocity. And so we're going to use Vx equals LIM, which is just the change in time going toward 0. And so it's going to be change in x over change in t, which is going to equal dx over dt. And so we know the instantaneous velocity can be positive, it can be negative, or it can be 0. When we look more toward instantaneous speed, we're going to be looking at the magnitude of the instantaneous velocity. So they go hand in hand. And when we think about instantaneous speed, I want you to remember that it has no direction associated with it. So velocity and speed will indicate instantaneous values, and the average will be used when the average velocity or average speed is indicated. And so there's many models that you can look at in order to help you solve different solutions. And so if we were to look at something underneath what we call constant velocity, this would mean that our instantaneous velocity during a certain time interval is going to be the same as the average velocity during that time interval. And so that was represented by Vx equals Vx comma average. So our mathematical representation would be the change in x over change in t, or our final velocity minus our initial over our change in